Today, we're honored to have Alexandros Eskenazis visiting us from Paris, and he's going to talk about learning low-degree functions on the discrete hypercube.
Okay, many thanks. Thank you for the invitation, and thank you all for coming. Now, this is meant to be a general audience, sort of genuinely easy talk, so please interrupt me with whichever question. It's a talk about a problem in theoretical computer science, but somehow the main goal is to highlight a connection with some very classical analysis, and I hope that this will be clear by the end. So let me start the way I start somehow 90% of my talks, which is a crash course on analysis on the discrete hypercube. So what's the hypercube? The hypercube is a 2-point set -1 raised to the power n. And you know, there's a finite abelian group, and therefore we can do elementary Fourier analysis on it. So this is a group with 2 to the n points, and therefore it has 2 to the n characters, which are this ws here, and you'll see that s is indexed by the subsets of 1 up to n. So that's why we have 2 to the n characters. And what is the character ws? It's a function defined on the cube. So ws of a point of a vector of plus minus 1s is the product where I belongs on the subset of those coordinates xi. Okay, so it's a some coefficient here, some basically Fourier coefficient, times a character. And what you can easily observe is that if you take ws and ws prime, and you multiply those and take the expectation with respect to the uniform measure, these are pointwise orthogonal. So, sorry, these vectors are orthogonal. So the expectation ws prime is equal to a 0 for s different than s prime. And therefore, this is an orthonormal basis, and as such, it also generates the space as we have 2 to the n of those functions. And since it's an orthonormal basis, we also have a very clear expression about what the Fourier coefficient is, right? So the Fourier coefficient is simply the dot product in L2 of the uniform measure of f times the character. Okay, so every expectation in this talk is going to be with respect to the uniform measure. So what I want you to notice is that this function here, ws, is not just a character in the group, it's in fact a polynomial whose total degree is the cardinality of the subset. And in fact, it's not any polynomial, but it's actually a multilinear polynomial, in the sense that we don't have terms of the form xi squared, since xi takes the values plus and minus 1. So this says that every function on the cube admits an expansion, which is in fact unique, as a multilinear polynomial of degree, of course, at most n, since, you know, xi squared is equal to 1. And so if we have a number d, which is smaller than n, we're going to say that f has degree at most d, if the Fourier coefficients corresponding to larger subsets are actually equal to 0. Okay, so there's a notion of an algebraic degree for functions on the cube. And having defined this, let's just move on to the main subject of this talk, which is the problem of learning. So the problem is the following. We are given a class of functions on the discrete cube -1 to the n. So what could this be? This could be the functions which are even, the functions which take, you know, the value something at the given point of the vector of all ones. It could be the functions of degree 1, so all the linear functions or whatever. So this is a class which we know explicitly from the beginning. But we also fix a function from this class which we do not know. And the problem of learning is the following. Having access to data of this form, so a bunch of points on the cube, comma, the value of f at those points, so knowing a bunch of points and the value of f at them, we would like to algorithmically basically guess what the function f is at a different point. So what we want to do is that we want to construct a hypothesis function, which ideally is equal to f, or at least approximates it well, but only based on this kind of data here. And this is a well-formulated mathematical problem, provided that I do 2 things for you. First of all, I tell you what well approximates means. And secondly, I just explain how we are getting access to this data. So let me just start with the second question. So there are many models for learning. We're just going to focus on the 2 most basic ones in this talk, and in fact just one of the 2. The first one is the query model, in which case the algorithm can sequentially request any selection of samples x1, x2, and so on. What does this mean to sequentially request? You basically, you know, at step 1 you have 0 information. So x1, no matter what the unknown function is always going to be the same point. And then you know x1, and you know the value of f at x1. And based on this information, you decide what's the second point that you ask. And then you know the value of f at x2, and you ask for x3, and so on. So this is the consistency of the algorithm, right? So this is the first model. So we sequentially request the samples, And the model that we're going to be more interested in for this talk is the random example model. In this case, the samples are IID random variables, each of which is uniformly distributed on the cube. So at each step, we choose a random point, and then we learn the value of f at that point. And notice that now this is a probabilistic model, right? So we could be extremely unlucky, and for the first kind of billion draws, we draw exactly the same point. So we have to add one more quantifier, basically, because the output function is random, and as it depends on the random sample. So we would want to construct an output which is a good approximation with high enough probability. Okay, so these are the models. Any questions? Because this is...
Sorry, when you say the samples are random variables.
Yes.
So your output is you take a sample and you get f, or do you get the expected value of f on some distribution?
No. So x1 is a sample from the uniform distribution, and then you know the actual value of f at this random point.
And you know the x1.
Exactly. You know both the vector.
And then you will get to know x2 and the value.
Exactly. Any other questions? Okay. So the question that we're going to be concerned with in this talk is how many samples do we need to actually make an educated guess? And I should say here, I'm not going to talk much about this, but we want an answer that's kind of algorithmic and not simply information theoretic. So it's important that you know whatever algorithm we create is actually reasonably efficient, and if you want towards the end, you can actually ask me about that. So there are interesting running time questions about algorithms of this sort. But we are going to be concerned about the number of samples. And just to set up the notation, in the query model, so in the deterministic model, we're going to denote by Q of the known class and an error parameter epsilon, the number of queries, such that we can output a function f which approximates, a function h which approximates f in L2 up to epsilon. The square here is the annoying computer science notation. And this is L2 of the uniform measure, always. And in the random case, you have this QR parameter, R stands for random, and we need to add one more quantifier here because we want to construct a random function such that it's an epsilon approximation of f with probability at least 1 minus lambda. Okay? So these are the parameters that we are going to want to minimize. And let me just make a completely trivial remark, which is that you need some structure. So it cannot be that your class is absolutely all functions and you expect to get a reasonable answer, right? So if your class were all the functions taking the values zeros and ones, even if you had 1 minus epsilon times 2 to the n values of an unknown function, you still have a lot of freedom, right? So if you think of the hypercube as this line segment, so here is 1 minus epsilon times 2 to the n, here is epsilon times 2 to the n, and suppose that you know your function exactly here. You know exactly how it behaves. So on this unknown interval, there are still two functions, one which lives here and one which lives here, which are epsilon apart in L2. So only with this information, you simply don't have enough to make a guess that's, better than epsilon in the error of approximation. So you do need some information on the structure of the class. And what is, philosophically the thing you need? You want, just by knowing the value of f, the values of f at this large or reasonably small, depending on the class subset, you want to be able to extrapolate the values at the remaining points. And
a quick question. Do we require our age to be in the class?
Not necessarily. That's a good question, but not necessarily. So yeah, that's interesting because for some cases we can attribute, for some cases we cannot. But it's a good question. So we want to be able to extrapolate the values from few points, and a class for which you ideologically believe that this is doable is the class of polynomials, right? Because for polynomials, even in the real line, we know that we can characterize them by a few values. So a degree D polynomial can be characterized by D plus 1 values. So the first class that was rigorously studied is this class f and d, which is a class of all functions taking values between -1 and 1, which have algebraic degree, as we discussed earlier, at most d. Now, what's up with this normalization here? We have an error epsilon, so we don't want a problem that's scale invariant, right? So we need to have some normalization in our functions, and we're going to see later on that's actually extremely important for this problem to have an L infinity normalization rather than an LP for any finite p. Okay, so the fact that it's bounded everywhere by 1 is actually going to be important for all the results that we're going to get. And just to familiarize ourselves with the notation, let me just prove a toy result for you. So if we want to learn a function from this class with error 0 deterministically, we need to perform exactly this number of queries. The sum of n choose j, j goes from 0 to d. And now why is that? Well, you know, if you wanted to learn a polynomial, what do you have to do? You have to choose your favorite point and learn the value of f at that point along with the values of the first d derivatives at that point. And then you know the polynomial. So as it turns out, you can do exactly the same on the cube. So if you have one point and you know all the derivatives of up to level d of that function and your function is degree d, then you can actually learn the full function. But what's a partial derivative on the cube? Well, I'm just going to say this, not write it. The partial derivative at some point of a function f, say ith partial derivative, is f at that point minus f at the neighbor which is connected by the ith edge. Okay, so every point has n neighbors, and therefore the partial derivative measures that. And you can iterate this operator and so on. So if you learn all the partial derivatives at a given point, then you actually know the function. All the derivatives are up to order d. And to do this, you have to concatenate these difference operators, and therefore it suffices to know every the value of f at any x which differs in at most d coordinates. And therefore this shows you that with this number of queries you can actually learn your function. And of course if you had fewer queries, the system would be underdetermined, right? So this is also exactly the number of unknown Fourier coefficients, and therefore you need at least this number. Okay, so this is a little combinatorial argument, just familiarize ourselves with notation. But in this talk we are mainly going to be interested in the random case and in the case of positive error. So it's going to be analytic rather than algebraic. And the first result, which is also one of the somehow historically first results of this area, is a so-called low-degree algorithm of Linial, Mansour and Nisan from 1989, who proved that if you want to randomly learn f and d up to error epsilon with probability 1 minus delta, you need to pay exactly this number of queries here. And I should say already, the main enemy in this talk is going to be the dimension n. Okay, so dimension n is the main enemy, and this is roughly n to the d times log n, up to dependence on the other parameters. And what I want to do is that actually I would like to show you the proof, because A, it's extremely beautiful, but B, it's also going to be useful for us because we're going to discuss refinements of this estimate here. So, so here's what we do. Let x1 up to xq, we don't know what capital Q is yet, be IID random samples from the Hamming cube. And you know, the information that we have on the unknown function f is spectral. So we're going to try to make a spectral guess on what the function should be. So remember, what we're looking for is the Fourier coefficient f hat of s, basically, which is the expectation of f times Walsh s. So what's the best thing that we can do? We can actually substitute it for its empirical counterpart. So we just know the values capital X1 up to capital Xn, along with the values of f there. So what we're going to do is that we'll consider the empirical Fourier coefficient. So 1 over q times the sum f of xj, Walsh s of xj. Okay, so this is the empirical Fourier coefficient. And notice that, you know, the function, the variables x1 up to xn, up to xq are independent. And therefore what we see here is an average of IID random variables. And moreover, the expectation is equal to the actual Fourier coefficient. So you take the expectation with respect to capital X here, this is the actual Fourier coefficient. And finally, because we assume that our function f is bounded by 1, this random variable here is itself bounded by 1. Okay, so of course, you know, by the law of large numbers or something, we believe that this is very well concentrated around its mean. And this is formally true, because all the random variables are bounded, we can apply the Chernoff bound, which tells us that the probability that the empirical Fourier coefficient minus the actual Fourier coefficient is bound below by a parameter b. The probability that this happens is bound above by 2 e to the minus q b squared over 2. So it has a Gaussian tail. And of course, the larger the q is, the better this bound becomes. So the more samples you get, the closer you are. And then, let's just apply the union bound. If we want the empirical and the actual Fourier coefficient to be b close for every subset S, each of those is bounded from below by 1 minus this probability here, and therefore by the union bound this is bounded from below by 1 minus 2 e to the minus qb squared over 2, which is this probability, times the number of those subsets. And this is the number of subsets of 1 up to n with cardinality at most d. And if we want this probability to be at least 1 minus delta, well, this forces upon us what q has to be. So q has to be this number, 2 over b squared times this log. And you see that this parameter here, whatever is in the parentheses, log of that behaves roughly like log n. So what's the name of the game now? We have this 2 over b squared. We want q to be small, and therefore we want b to be large. So we need to choose a large b such that the approximation given this assumption here is still good enough. Okay, so what's our guess going to be? Of course, a hypothesis function, rather than the sum of actual Fourier coefficient times walls, is going to be the sum of the empirical Fourier coefficient times walls. And then we're going to estimate in the high probability event the L2 difference from f to this hypothesis function by the Parseval identity is just the sum of Fourier coefficients squared. And each of those, by the assumption, since we are in that high probability event, is bound above by b squared. Okay, and there's also this many of them. So if we want this whole L2 error to be smaller than epsilon, we just have to choose b squared to be this number. And so this is epsilon divided by n to the d roughly. And if you plug this into the previous formula where we had a 2 over b squared, this gives our n to the d log n bound. That was the point of the low-degree algorithm. So I just proved for you that in n to the d log n samples, you can actually learn a low-degree bounded function.
Is it the request query in this theory? That you said you first choose x1?
No, in this case, the samples are uniformly at random. So x1 is random, and then x2 is independently random, and so on. So this is for the random model. Any other questions? Okay. So the question that we want to address is whether n to the d log n samples are too many. I should say that this n to the d log n has somehow probabilistic interpretation. So n to the d is the dimension of the space of low-degree functions. And then you have to take into account the fact that you may be having repetitions, right? So you may be given points that do not offer you any new information. So for this, n to the d times log of n to the d roughly, kind of conceptually, there is some explanation for it at least. And a result, this is not historically the right order, but a result which highlights that this might not be the case is something which we proved with Ivanisvili and Streck. This is not a very hard theorem, but it says that you can in fact learn this class randomly without error in n to the d log n by paying an additional, a slightly worse factor of d. Before it was something like d, now it's exponential. But algorithmically this is not maybe as interesting, because anyway we're going to be focusing on the case of positive epsilon. And what first got us interested in this problem was this result which appeared last summer of Ayer, Rao, Rice, Rotvas, and Yehudayev, who proved that this n to the d log n can actually be improved to an n to the d minus 1 log n. So you can shave off a little power of n, but this has a conceptual meaning, as we said, since you go below this barrier of the dimension times log the dimension. And what I want to talk about today is basically the correct order of magnitude, which is substantially smaller. So in fact, there is no polynomial factor of n. So the correct number of samples is simply log n. And that's something that we proved with Paata Ivanisvili last year. And just before we start discussing this, let me just make a comment, which was from our follow-up paper mentioned before, which is that this factor log n is in fact also necessary. So this is a fairly easy information-theoretic lower bound for this quantity. But what makes it harder is to track in this lower bound here the dependence on d. So we are going to get back to that. But if you just want to prove a lower bound of log n, that's not extremely hard. But with the correct dependence on d, it becomes harder. Any questions about the? Good. So as I said, I'm going to speak about the upper bound. And you know, to figure this out, to figure out how we can win, we have to go back to the previous proof and see where we lost. And here's ideologically where we lost. The function f is bounded by 1 in absolute value, and therefore in particular it's also bounded by 1 in L2, which means that the sums of squares of Fourier coefficients is bounded above by 1. Now remember that b squared, we chose it to be like n to the minus d, but now we would want to choose it as something that's substantially bigger. So imagine that we have b squared to be greater than n to the minus d. Then what we were doing before is that we were approximating this number here by a number alpha s squared, which was n to the minus, which was b squared away. Okay, that's what was happening in that proof. On the other hand, here we are summing up n to the d numbers, and we're getting something which is smaller than 1. So what's happening is that we're summing those n to the d numbers. A lot of them are smaller than n to the minus d, and we are introducing an error of approximation which is actually asymptotically larger than n to the minus d. So we have an estimate in which the error term is much bigger than the actual quantity. And of course, that's not a very smart thing to do. So we lost by incorporating all the empirical coefficients, and what we should do is to make sure to include the few ones which are influential, so the ones which are bigger than a parameter a. And how many of them are there? Well, the number of Fourier coefficients which are bigger than a is bounded by 1 over a squared just by Markov's inequality, since the squares of those sum up to 1. And if you run this kind of argument, what you're going to be stuck with is to estimate a term of this form. So you are going to take the sum of Fourier coefficients squared over those Fourier coefficients which are smaller than a. And what you would want is for this quantity to become kind of small as a becomes small. Okay, if you complete somehow this plan. And I should already say that this is a very important point where uniform boundedness plays a role. So for instance, consider the function on the cube, which is x1 plus x2 plus xn divided by square root of n. This is a function all of whose finite pth moments are a universal constant depending on p. But if you look at this sum for various values of the parameter a, the moment a is bigger than 1 over square root of n, this sum is simply 1, and then it just bounces down to 0. So this is a function that's bounded in null LP space, it's not bounded in L infinity, and it simply does not satisfy a condition like this. And this is something that's called the Fourier concentration condition. So it's going to be important that the function is bounded in L infinity in order to get an estimate of this sort. So how do we get an estimate of this sort?
I'm confused about the idea.
So, yeah, okay.
So, you're trying to only use a larger Fourier coefficient.
Yes.
We know which ones are larger.
I don't know yet. It's, we're going to get to it. So it's going to come in the proof. So part of the difficulty of the proof is figuring out which Fourier coefficients are large. But you know, if we believe, okay, it's a spoiler, but if we believe that if we know that all Fourier coefficients are close to the empirical counterparts, then we just have to check which empirical ones.
Close to what?
To their empirical counterparts, so to the empirical Fourier coefficient, which only costs us a log n. Then we just have to check the ones for which the empirical ones are large. But we're going to see it in the proof. It's going to come up in a few slides. So let me digress by some very classical facts. So here's a triviality. If you take a linear form, sum ai xi, and you take its supremum over all vectors which are bound in L infinity norm by 1, what this is the L1 norm. It's a triviality. Something which is not a triviality is what happens if you replace the word linear in this sentence. So that was actually a question of a mathematician called P.J. Daniels in the 20s. So you have here a bilinear form, sum ai xi yj, and you can assume that only the xi's and the yj's are bounded above by 1. So this is definitely bounded above by the sum of aij absolute value. And this guy asked whether you actually have a reversal to that. And Littlewood very famously responded that this is not the case, but actually found the correct counterpart of the inequality. So this is Littlewood's famous 4/3 inequality, which says that this supremum here, for a bilinear form, is bounded below by a little LP norm of the coefficient, but for some p which is not 1, it's actually 4/3. 4/3 is just sharp, he proved it also in his paper, and square root of 2 is also the correct constant. So the moment you have a bilinear form, you can control its norm from below by this little LP norm of the coefficients. And now the connection is not yet clear, but I should say that didn't take long. Just a year after, Bonenblust and Hille found the correct counterpart of this inequality for general polynomials, and this was important. They were motivated by something in analytic number theory, actually. So the Bonenblust-Hille inequality tells you that if you have a degree d polynomial of this form, so basically here I am not constraining the number of variables like in the previous statement. So alpha here is a multi-index, alpha 1, alpha 2, and so on of natural numbers. The cardinality of alpha here is just the sum of the alpha i's, so the total degree of each monomial. and x to the alpha is x1 to the alpha 1, x2 to the alpha 2, and so on. If you have a polynomial like this, then its supremum is bounded below by a constant depending only on d times this little LP norm of the coefficients, but P now is this number 2D over D plus 1. So it's a number that's slightly smaller than 2. It converges to 2, but slightly smaller than 2 for any individual degree. Of course, for D equals 1, that's 1. For D equals 2, it's 4/3. Okay, and again, this is the sharp exponent. I should say that this constant CD here, this has been out for more than 90 years, and this constant CD is a major mystery. So, first of all, it very strongly depends on the field that you're working with. So the real constant and the complex constant are actually different. So if you denote by CD of R the constant for real polynomials, then CD of R to the 1 over D is known to converge to 1 plus square root of 2. So this constant grows exponentially for real polynomials. On the other hand, the complex constant, by which I mean the constant for which you have this for analytic polynomials on the complex plane, just polynomials of Z, not Z bar, is known to be sub-exponential. So grows at most like e to the square root of D. Okay? And so you see, the real constant is much larger than the complex constant, and in fact it's a major open problem for about 100 years whether this constant is actually polynomial in D. So this is simply not known. For this inequality, complex polynomials. So this is a very famous open problem in approximation theory. But I don't want to talk about that. I just want to focus on the following very simple things. Now I'm thinking about the real constant here. And suppose that P is the multilinear polynomial representing a function on the Hamming cube. Okay? And just apply this inequality to P. Now, here we are taking the supremum of P on the solid cube, but P is a multilinear function. So of course the supremum is attained at one of the vertices. So what we have on the right-hand side is simply the L infinity norm of f, and what we have on the left is this LP norm of the Fourier coefficients of f. So this is in fact an inequality which, restricted to multilinear polynomials, becomes an inequality on the hypercube.
Can I ask one question?
Mm-hmm.
I know it's not really related to that, but is there an intuitive way to see that these two constants should be different? I mean, it seems like these are just polynomials. Is there an intuitive way to see why the concept?
So it's clear that one should be bigger than the other formally, right? But right, because here you're just looking at fewer polynomials but yeah, don't think I can offer something much better than that. This constant somehow has a lot of has much nicer symmetry. So there's a very simple, nice trick that says that here the constant over all polynomials is the same as a constant over all homogeneous polynomials. So the first reduction here is to very easily reduce it to homogeneous. And that's because you're talking about stuff on the torus, so you can introduce an extra variable and homogenize it or whatever. Here already, if you talk about the homogeneous constant, converges to a different number that's between 1 and 1 over 1 plus square root of that. So the moment you start working with this, you see a lot of technical difficulties. But I don't have somehow a one-sentence explanation. Okay, so that's...
Yeah, fewer polynomials to the lower case.
Sorry?
Why was there fewer polynomials to the lower case?
Because here you are talking about polynomials on C, so meaning, if you think of Z as x, y, it's only polynomials of Z and not Z bar, just the analytic polynomials. Any other question? Okay. So this is our inequality. This is going to be our technical tool. And let's just prove the bound for the queries. So let's just go back. This idea, I should say, goes back to Koshulevich and Mansour, the idea of introducing a cutoff in the spectrum, even though it's fairly standard also in statistics. So again, we fix a B. This is our Q. And the probability that the empirical, I haven't changed anything. And now I'm going to change something. And what I'm going to change is that now I'm going to figure out which are the subsets which carry a lot of weight. So how do I select the subsets for which the Fourier coefficient is large? And what I do is that I consider the subset for which the empirical Fourier coefficient is bigger than 2 times b. Okay, I don't know the actual Fourier coefficient, therefore I don't know at which subsets the actual Fourier coefficient is big, but I do know on which ones the empirical Fourier coefficient is big. And since I am on the high probability event, the Fourier coefficient and the actual one are just b apart, the empirical and the actual are b apart, so when the empirical is large, then the real one is bigger than b, and when the empirical is small, then the real one is smaller than 3b. Okay. Here I just use that fb minus f hat of s minus alpha of s is smaller than b. And now what we're going to do is that we're going to make our guess not to be the sum of all the empirical Fourier coefficients, but just the sum of the influential ones times Walsh. And we're going to estimate f minus the guess L2 norm squared. And what we have is the sum over the important subsets of the difference of Fourier coefficients squared, plus here the sum over all the remaining subsets of Fourier coefficients squared. Okay? And this kind of completes the philosophy which we had, right? Because here our philosophy was that we have few subsets for which this difference is small, and here it's this Fourier concentration condition that was on the previous slide. Just control each of these terms separately. Now let's just start by proving that there aren't too many subsets here. I could do it with Markov's inequality like on that slide, but actually let me do it with the Bonom-Lucille inequality. So how many subsets are there? Well, since each Fourier coefficient is bounded by b, I can apply Markov with this weight here. So it's this L2d over d plus 1 norm divided by b to the minus 2d over d plus 1. And this is just a constant depending on d times b to the minus 2d over d plus 1. And now I am summing this many terms, each of which is bounded above by b squared. Okay, and therefore when you multiply this by b squared, you get this constant depending on d times little b to this small power here. So this controls the first term by something which depends only on d and little b. And for the second term, it's, well, just as easy. So you are summing over subsets for which the Fourier coefficients are small, the L2 norm. So what I'm going to do is that since each of those numbers is bounded by 3b, I'm going to pull out a little power from the 2 here. So I have 3b to the 2 over d plus 1. And here I'm summing this 2d over d plus 1 powers of f hat of s. And this whole sum actually converges, and the constant depends only on d. So again, we have this number depending on d times b to this power 2 over d plus 1. So you add those together, and you get that the L2 error of approximation is a constant depending on d times b to this little power, and therefore you have to choose your b squared, and that's the upper bound that you get for b squared. So you notice that here there is no dependence on n, it's just a bound depending on d, and this Bonom-Lucille constant. And that's the end of the proof, basically. You plug it in. So let me just recap where we are. So we have this upper bound of log n. I just showed you the proof. There is, as I said, an information-theoretic lower bound, again by log n. And if you plug in and somehow see what the bounds gave you, there's this log n over delta everywhere. Here you have a bd to the power 2d. And on the lower bound, the non-trivial part is this factor 2 to the d here. If you want to just get the factor d here, it wouldn't be so hard. And the dependence on epsilon is very different on the upper and the lower bound. Now, the best known bound for BD is actually the same as the complex bound. So let me just go back to this a little bit. So BD was bounded by the real constant, which we believed grew exponentially. But in fact, it's not the same because it's only restricted to multilinear polynomials. And what the Fant, Mastilo, and Perez showed in 2019 is that if you restrict the real constant to multilinear polynomials, you again get a sub-exponential behavior. And in fact, it's not even known, it could be that BD is simply a universal constant on the hypercube. So it could be that BD is equal to 2. That's the best lower bound that we actually know. So if BD was a universal constant or even polynomial, you see that the behavior on D of this part would be very comparable to the behavior on D over here. Okay, so the behaviors on D are also reasonably close, just conditional on some well-known open problems. And the dependence on epsilon can also be improved if we a priori knew that the unknown function is Boolean. Any questions about the thing? Okay, so let me just recap and see where we are. So what's the advantage of what just happened? We just found the correct query complexity for the class of bounded polynomials. What's the disadvantage? Well, this was just one class, and it seems like this argument is extremely rigid somehow. We really used, by using the Bonom-Lucille inequality, the polynomial structure very, very strongly. And basically when we wrote our first paper, the main question which we got from many people is, what happens if you tweak the polynomial condition and you deal with approximate polynomials. There are reasons motivated from applications actually for that. So what's going to be an approximate polynomial for me? There's going to be now this f and d with an error parameter t. So we're still speaking about bounded functions in L infinity, but we assume that the sum of the squares of Fourier coefficients for weights greater than d is actually bound above by t. So what this means is that you are t or square root of t, depending on the normalization, apart from a degree d function. But here I should emphasize that the main difficulty of dealing with this class is that if you perturb the spectrum to make it low degree, there is no guarantee that the function that you are going to get is going to remain bounded in L infinity. So you are bounded and you are close to a degree d function, but you are not close to a bounded degree d function. So there are two different things. And the theorem which we were able to prove with Ivanisvili and Streck is that there exists a parameter eta depending on t and d, such that we can have the same logarithmic upper bound on the queries. I'm not going to write down all the dependencies now, but the error of approximation does not start from zero basically, but it starts from this constant eta. And this requires a different proof. But you should take into account that the class of all functions which are bounded by -1 and 1 is just a metric space of diameter 2. So if this parameter eta here is 3, and you want to learn up this earth, then this theorem is meaningless. So this is meaningless unless I tell you what eta is. Well, the good news is that if you keep d fixed and you send t to 0, then actually eta of t comma d goes to 0. So this is reasonable. But just to be more concrete about the estimate, I want to speak about the class which I'm going to denote by b and d of t, which is the class of t approximate polynomials, which in fact are Boolean. So they just take the values -1 and 1. So if they take just the values -1 and 1, first of all, this is just as interesting for most of the people doing applications. And secondly, we have somehow much better estimates for certain parameters. So let me tell you what the theorem is. Now, if t, the error parameter, goes to 0, like slower than 1 over faster than 1 over square root of d. So if it's 1 over square root of d log t, then the logarithmic bound works fine. Okay, so if t and d are related by a condition like that, then you have the correct logarithmic bound. Notice that the theorem I proved for you was just for t equals 0. Okay, so here you have somehow an upper bound for t. What's kind of shocking to me is that this is sharp. So if t is at least a universal constant times 1 over square root of d, and you want to learn with some fixed error and some fixed probability, then there are chances that you're going to need at least 10 queries. So here there's a sharp phase transition on how many queries you need, just depending on the window of approximation by a low degree polynomial and the degree d. Okay, so there's a phase transition like this. And any questions? Okay. And I want to end by presenting two examples of classes of approximate polynomials for which this is useful. And the first class is the so-called linear threshold functions. So a Boolean function is a linear threshold function if it is of the form sine of x dot theta, where theta is a fixed vector in Rn. So what's happening here is that we are in Rn, we have a hyperplane, theta perp, and our function is just 1 here and -1 here. So what's happening is that we keep getting points from the cube. Some fall on this side of the hyperplane, some fall on the other side of the hyperplane, and we need to understand what the hyperplane was, or at least what the function was, because you can imagine two hyperplanes being really close, and depending on whether they're situated, to define the same functions on the cube. So that's what a linear threshold function is. And if one wants to understand how close a linear threshold function is to a low degree polynomial, there's a sharp theorem which is called Paris noise sensitivity theorem from 2004, which asserts that if you want to be t close, there's a square here. So if you want to be t close in L2 from a function of degree d, then d has to be a constant divided by t squared. Okay, so it's a constant divided by t squared for t approximation. And if you go back, so our d here is 1 over t squared, so 1 over square root of d is exactly equal to t. So this is a situation in which, if you go back in the previous slide, we are exactly here. So t is exactly of the order of 1 over square root of d. and therefore our theorem does not apply. So you don't get a reasonable bound for this class. And in fact, this is for a good reason. This is exactly the class for which we could prove, and it's actually very standard, that you need at least n samples to learn it. But here's another class for which you can actually learn it efficiently, and this is actually, this was kind of the main application, initial application of the low-degree algorithm, if you read the Lineal Mansour and Nisan paper. So a DNF formula is a logical OR of terms, each of which is a logical AND of Boolean variables. So what's happening here, this here is a Boolean function. So x1, x2, x3 are the variables. When is this function equal to 1? If either x1 and x2 are 1, or x2 and x3 are -1, or x1 is -1 and x3 is 1. Okay, this defines a Boolean function on the cube, and the size is going to be the number of parentheses here. So the size of a DNF is the number of parentheses. Okay. And if you want to study, this has been studied for a long time, and it's a very interesting question. Again, there's a square here, how the Fourier spectrum of a DNF concentrates. If you want to be t apart from a degree d polynomial in L2, then your d has to behave like log the size divided by t to the power 2. So if you think of the size as constant, or not horrible in terms of t, then your d here actually behaves logarithmically in 1 over t, and therefore definitely t is little o of 1 over square root of d. So if you go back to the previous phase transition, this is definitely in the favorable domain that you can learn from much, much fewer samples. So that's what I want to say. Let me just close maybe with a couple of problems that I think are interesting. So let me just close with two classes of functions for which there are very interesting open questions about what to do. So the first class is again the class of linear threshold functions that we discussed before. So it's all functions of the form f of x equals sine of x theta, where theta is a vector of the sphere. So I told you, without proving, that we need at least n samples to learn this. In fact, we know this is simple and standard, that if you want to learn this, I'm going to omit the dependence on epsilon and delta here. You can also do it in at most n. So in fact, this is an equivalent. You know that you need roughly n samples to learn this. But what's open here is the running time. So if you want to construct an efficient algorithm that does it, the conjecture is whether it can be learned in time, which is n squared times polynomial of 1 over epsilon. There's something that's related to what's called the Chow parameter problem in Boolean analysis and learning. And this n squared again is not very hard, but getting the correct dependence on epsilon in this problem, which we majorly disregarded in our algorithm, if you saw there's a 1 over epsilon, the d, and so on. This has been a somehow very this has been a very interesting problem for a while, and many people have thought about this. And the current status is a quasi-polynomial here. Quasi-polynomial, something like e to the log to some power. The second question, which we don't know anything basically about, or I don't know much about, is the class that's called the polynomial threshold functions of degree d. So it's all functions of the form sine of p of x, where p is a polynomial of degree d. And we have no idea about sensible bounds on the sample complexity of this object. I think n to the d is a fairly easy upper bound, n is a fairly easy lower bound. But here you see what's happening, if you think of the analogy with this picture, is that what we do is that we separate the plane by a polynomial curve of degree d. We separate, Rn by a polynomial curve of degree d, and we know on which side you are, we know the sign of the polynomial on a given point, and we need to understand how many samples we need to basically figure out the polynomial. And I don't know of any sensible bounds or guesses about this. That, Thank you so much.
Are there more